All right, welcome to the Chapter 8 Epoxide lecture. We'll get started in a sec. Let's get my pen set up and let's review what an epoxide is. This is section 8.4. What are epoxides? A second. All right, so epoxides are cyclic ethers, and they're special. They have angle strain or ring strain. Ring or angle strain. This matters because it's going to give a controlled ring opening. Okay, there's hydrogens there. We'll see these reactions. So let's see how we make these first. You won't have to draw this. This is a teaching mechanism as opposed to a test mechanism. Well, let's show it so that you can see how you can predict products. We have an alkene. We're going to go to an epoxide. This is actually a meso compound. If you draw the opposite stereochemistry, where both the oxygens are on the same face but up towards you, then you'd have the same molecule. It's a meso compound. But how do we make this? Let's see this reagent a couple times. Maybe not, just one time. We want to predict products. I gave you the product, but this is going to form an epoxide from an alkene. And the way we think about this, I'll draw it down here. Here's our alkene redrawn. With this peroxy acid, we call it. So instead of a carboxylic acid, it's called a peroxy acid. There's all the lone pairs. We're going to use 4 arrows to show this all at once, but I'm going to kind of talk you through it. I'm going to say some things verbally without drawing so that you can understand this peroxy acid. Peroxy acid. So instead of acetic acid, it's peroxyacetic acid. It's got an extra oxygen. And this oxygen is what's going to get transferred. I'm going to shade that one. That's what's going to get transferred. And I'm going to show you how this is done. So verbally, I'm going to tell you that this hydrogen, here I'm kind of circling it without drawing. This hydrogen is being drawn to the carbonyl by hydrogen bonding. We talked about hydrogen bonding. This pair of electrons is interacting with this H, not forming a bond, but an interaction, a hydrogen bond, in which it's stabilizing its structure here. So it's a ring type structure. If we wanted, we could draw a little dashed line there to indicate that. It's kind of rigidifying this peroxy acid. And what that means is that this oxygen-hydrogen bond here is a little bit weaker. So this oxygen here is electrophilic, which is weird. Typically, oxygens have lone pairs. They're nucleophilic. But this group here can be thought of as a leaving group. This whole group that I'm circling, we thought of a leaving group from this oxygen. So we can see this pair of electrons on the alkene reach out and grab the oxygen. This is leaving to form an oxygen-carbon double bond. This is going to reach out and grab that hydrogen. We'll see the products of this, the byproducts. And then this pair of electrons has to reach out and grab that carbon. It's different. It's a lot going on. We can say this is concerted. Okay. And all of this happens, and we get transfer to form the epoxide. So these pi electrons on the alkene are attacking the oxygen. At the same time, these electrons are attacking that carbon, and then all this is happening. This is leaving, and it's going to pick up that hydrogen, and here's our byproduct, acetic acid. Okay. So you should be able to predict the products of these and sort of notice that this shaded oxygen is going to be transferred, and this is a byproduct. Okay. So that's one way to form epoxides. Let's look at a way to open them selectively. So we're going to use that epoxide that we made. We're going to add H2SO4 and water. And we're going to get a set of enantiomers. Trans diols. You get a racemic mixture of these two enantiomers. They're called diols because there's two of them, and they're trans because they're on opposite faces. I want you to recall something. Recall the bromonium intermediate. We looked at this in chapter 5. We looked at it again in chapter 7. When an alkene is reacted with bromine, you get a trans dibromide. You get very similar looking products as up here are these diols, but they're bromines. Okay. So what do H2SO4 and water form? Let's show water interacting with sulfuric acid. Protonating to give this active acid over here. With the sulfonate, which again is a spectator. That O- is a spectator, and now this oxygen can protonate. Going to protonate to form a protonated epoxide. With our sulfonate, water is generated here. Again, you won't have to draw this mechanism. So we'll call this a teaching mechanism. Okay. But let's redraw the epoxide over here underneath each of these diols. Okay. Either carbon can be attacked, and it's going to attack from the top of wherever it attacks. Remember, there's an H here that we're not showing. So this is SN2. This step is SN2. First, you get protonation of the epoxide, and then SN2, ring opening. SN2 meaning substitution, nucleophilic second order. It's a concerted transition state. The water is attacking, pushing the electrons up to oxygen. Think of this as a leaving group. This OH here, this oxygen carbon bond, the oxygen's leaving that carbon. So it's going to attack from the front face that's less sterically hindered. I'm going to show this once. This gets busy, I know. This is the protonated form of one of these diols. So as water opens, again, there's excess water there. This is a catalyst. Then what can happen? The water can deprotonate and form the product and regenerate this acid. The acid is regenerated when this interacts. So there's excess water that acts as the base to get you here. And so this oxygen over here can attack from the front face, open the ring, right? There's a similar intermediate. Now the protonated form is on the bottom. And then you can see the same thing with water. Okay, so you get two products. They're racemic, and that means they're two enantiomers of one another. Again, go back to the bromination. Look at that bromonium intermediate. So the bromination that we talked about in chapter 5 and 7. Take a look at that again. All right, let's look at another reaction of an epoxide. This is a single enantiomer of epoxide. We're going to open it with NH3. So before I show the product, let's work through this mechanism. Think about how this is going to work. Which carbon, A or B, is less sterically hindered? It'd be B. Okay, the hydrogen is smaller than the methyl, and so SN2 ring opening using ammonia. This pair of electrons is a nucleophile. The nitrogen is a nucleophile. It's going to come from the top face, the bottom face here, where the hydrogen is, the back face, if you wanted to make that dash to kind of think about it. Again, another teaching mechanism. I want you to be able to predict products for all these. Opens it up. And now instead of protonating the epoxide first and having water open it up, now we just have ammonia attacking from the back face. We get SN2 inversion at that stereocenter. We get a minus charge on the oxygen. We get a plus charge on the nitrogen. Again, if we had a O minus and an NH3 plus and an NH4 plus, this O minus would attack that proton, pushing the electrons back. So your final product is an amino alcohol. Amine and an alcohol, amino alcohol. So that's a basic reagent that opens an epoxide. The last one was an acidic reagent that opened the epoxide. Let's look at another example of a basic. We're going to start with the same starting material. Before I move on, this is a single enantiomer. You get one enantiomer and you get one diastereomer. You get one product because of the angle strain or ring strain of the epoxide. Angle strain gives selectivity. Okay, by an SN2-like inversion, you get inversion at this stereocenter here, carbon B, and nitrogen attacks. So let's look at another basic nucleophile. Same idea. The less sterically hindered carbon is going to get attacked. And here we just have two steps. We have a sulfur nucleophile, and we're going to quench it with H3O plus Cl minus, let's say. So before I show the product, let's work through a mechanism. Single enantiomer. Step 1. Draw out your sulfur nucleophile. Pair of electrons is going to attack from the back face, opening up the ring. The O minus and Na plus associated with it. And then you have a sulfur carbon bond with 2 lone pairs. The hydrogen's on the same side as the oxygen. Now we're going to treat this with acid. Step 2. Draw out our H3O plus, Cl minus. Where would we get this? We would dissolve HCl in water, get dissociation. This O minus is going to pick up a proton and give the desired product. The OH SCH3. What's our byproduct? H2O and sodium chloride. So this is protonation with acid to give the alcohol product. Okay? Again, teaching mechanisms. All of these epoxides are teaching mechanisms so that you can learn how to predict products. We'll have to predict products on all these. All right, so we introduced sulfur there, and let's talk a little bit more about sulfur. That was epoxides. 8.5 are what are thiols? Thiols are much like alcohols in some ways, but different, as we would expect. No two functional groups are exactly the same. That's what makes them unique. But just like an alcohol with an OH, we have an sp3 hybridized atom, sulfur. Here, they're a little bit more acidic. Their pKa, this hydrogen's acidity, is about 8. Remember that the alcohols are about 16. Sulfur is a stinky element. It's used to dope your natural gas in your house so that if you have a leak, you smell a sulfide. And so sulfur in general is stinky. There's we're going to do, the only naming we're going to do is linear only. Very simple. We're going to learn CH3SH, for example, is methane. So it's just like methane, methane thiol. So really what you need to remember is thiol is the key word. It's methane thiol all the way down through 8, as we've been doing. 2, 3, 4, 5, 6, 7, 8 carbons, SH, octane thiol. 1 word, 2 words, whatever. It's 1 word. Octane thiol, okay? We'll also have, just for your information, actually, let me do this. So naming linear only for thiols and sulfides. We'll only get, just like ether, we're only going to do symmetrical sulfides. Sulfides are the sulfur equivalent of ethers. Okay, so no H. We have 2 groups. So this would be dimethyl sulfide, just like we did dimethyl ether, diethyl ether, dipropyl ether. We're only doing linear and symmetrical. Okay, symmetrical and linear. We're keeping ethers, thiols, and sulfides very simple. So we have dimethyl sulfide, diethyl, dipropyl, dibutyl, etc., all the way to dioctyl sulfide. Okay. And so that would just be 2 8-carbon chains on each side of the sulfur. Just for your information, a disulfide has a sulfur-sulfur bonds. This is a disulfide. And these are very important biologically. Biologically relevant. Okay? So that's just FYI up there. All this is an introduction to sulfur. You'll see some nucleophiles that are sulfur that we'll use. We won't do a bunch of other stuff with sulfur. You can oxidize sulfur with an oxidant, making a sulfur-oxygen bond. There's a lot you can do. There's a lot of biological importance that you'll learn in biochem if you take that. And but that's where we'll stop on chapter 8. We'll have a review tomorrow. We'll have office hours from 1:30 to 2:30, and the exam will still be Monday. So that ends the lecture. It's a short lecture. I didn't have that much more material, and we will see you tomorrow.